Welcome back to our lesson on bisecting. In the first video, we showed how to do the construction and proof for an angle bisector. And in this video, we'll do the construction and proof of the line bisector. Now, before you bisect a line, you need to have a line to bisect. So let's go ahead and draw a line. Go ahead and draw this in your notes, in your notebook, hopefully, dot grid. And don't draw it too high up on the paper because we'll need some space above and below this line. So I'm just going to go ahead and draw in the line. Oops, my straight edge is seeming to be not that straight. I might have to get another one here. Or maybe use a different side of it. Okay. All right, well, there's my line. And before I show you the construction, I always encourage you to give it a shot on your own. Maybe you already tried and that's why you're watching this video and you're like, well, I already tried and I want you to show me. Don't worry, I will. But if you haven't tried it, give it a shot on your own. Pause the video and then, after, you've given it a shot, come back and restart the video and I'll show you not just one, but 3 methods for bisecting a line segment. All right, welcome back. Let's look at our first method. As I said, I'm going to show you 3 methods for bisecting a line segment. The first method is what I call the double equilateral triangle method. So the first step here is to set the compass to be the length of the line segment. And then you're going to draw an arc all the way across like that. You could draw the entire circle if you wanted to. I'm just going to go ahead and draw that arc like that. And then go to the other side. Once again, make sure the compass is the right length. And now we're going to draw a similar arc centered at the other endpoint. Okay. And now we're going to take these 2 intersection points up here and down here and connect them with a line. So here we go. So there's our line, and this original line here has now been divided into 2 equal parts. In other words, bisected. The reason I call this the double equilateral triangle method is that if I connected, these 3 points here, and then these 3 points here, I'd have 2 equilateral triangles. Okay, so another method, this is actually a very similar method. Once again, we're going to start with a line segment. Okay, so there's my line segment. And this method basically says, you don't have to set it to be that exact width. You just have to set it to be more than half of the length of the line. And as long as it's more than half, you'll have the arcs you need to do the bisection. So I'm going to set it to be some length that's at least more than half and generally less than the full length of the line. But now I need to be careful that when I flip it to the other side, the compass keeps the same length setting. So I haven't changed the width of the compass. Okay. So then I make another arc there. And now I connect, once again, these 2 intersection points. And there we go. So that is dividing this line segment into 2 equal parts, bisecting it. But I promised you 3 methods. So let's do just one more method, okay? And in this method, we are going to, once again, start with our line segment. Okay, so there's my line segment. And I will once again set the compass to be the length of this segment here. Okay, and I'm going to draw, I'm going to sort of run into my other construction, that's okay. Draw that arc there, and now I'll center it at this endpoint. Draw this arc right here. Okay, but this construction method actually involves it involves bisecting an angle. So it actually builds on the last construction. So first thing we need to do is draw our equilateral triangle on top of the line segment. So we'll connect these points. This is just an equilateral triangle construction like we have from lesson 2. And now we're going to bisect this angle up here. So I'll go ahead and do the rhombus method, because why not? I'll draw an arc across here, and then keeping the same compass setting, I'll draw an arc across like that. And then setting it to this intersection point, I'll draw an arc across like this. And now I'm going to draw my angle bisector, which also happens to pass through the original line segment. Okay, so this bisects this angle, which that wasn't actually my goal. My goal was to bisect this line segment, and the angle bisector has actually done that as well. So now you can see 3 methods for bisecting a line. Typically, you'll use one of these 2 methods, not this method, but all 3 of them work. So now that we have done the construction, it's time to do the proof. I'm actually going to do 2 proofs for you, 2 for the price of 1. And the first proof I'm going to do is actually based on the angle bisector approach, the last one I did. And so here is my line that I'm starting with. Okay, we'll call this line AB. And so my given for this proof, given line AB. My goal is to bisect AB. Okay, so step 1 is going to be to construct an equilateral triangle on the segment AB. Now, I'm not actually going to go through the steps of constructing it. I'll just sort of eyeball it, but you know that we can do the construction. We did that just a few minutes ago. And so let's go ahead and just draw this in and say, okay, I have constructed equilateral triangle ABC. So this is the point C. So construct the equilateral triangle. Actually, I'll just use the triangle symbol here. The equilateral triangle ABC. And my justification there, of course, is I have a brick. I have a brick for this. Equilateral triangle construction, brick number 2. So brick number 2. Okay, now let's bisect the angle at C. Bisect angle C. I could say bisect angle ACB, but there's no other angle at C, so there's no ambiguity in saying just bisect the angle at C. And what is my justification there? Well, I just did it in the previous video, the angle bisector. So that was brick number 3. So brick number 3 says I can bisect an angle, and so let's go ahead and just draw the bisector in here. I'm not going to do the construction because we know that we can do it. We've already done it. So bisect the angle C. All right, step 3, we see we have an intersection point between the bisector and AB. So we're going to call that point D. And so define D at the intersection point. That, of course, is rule number 1. Rule number 1 says I can define or draw a point anywhere I want to. Okay, and now let's look at what we can say about this figure. So first of all, I can say that length AC is equal to length BC. So I'll say step 4, AC is equal to BC. How do I know that's true? ABC is an equilateral triangle, so definition of equilateral triangle. Okay, step 5. Let's see. Well, I know that this angle here is equal to this angle here. So let's write that out. Angle ACD is equal to angle BCD. And that is based on the definition of bisector. Since I constructed a bisector, I know it divided the angle into 2 equal parts. So definition of bisector. Okay, and then, well, we have CD on top of itself, so we know that equals itself. And so the thing is, I won't be able to use side, side, side here like I did in the previous lesson, because I'm trying to prove that AD is equal to BD, and if I knew it equal, if I knew they were equal, I wouldn't, need to, in order to use side, 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 I need to say that those two are equal. And if I knew they're equal, I wouldn't have to bother using side, side, side. So side, side, side is non-starter here. So we're going to have to add another assumption. And that assumption is that if the corresponding side, angle, and side of one triangle are equal to the corresponding side, angle, and side of a second triangle, then this triangle will be equal to this triangle. The two triangles are equal if the side, angle, and side are equal to the corresponding side, angle, and side. That is going to go under our other assumptions as yet another assumption that we need to make. So SAS stands for side, angle, side. Again, we might wish that we could prove this, and maybe we can, but for now, we're just going to go ahead and add it to our list of assumptions. Now, one thing you might wonder is like, wait, what if we just add everything to our list of assumptions? What if we just assume the angle sum of a triangle? You have a point there, if that's what you think. And these questions will be addressed later in this unit and the next unit. But for now, we're just going to go ahead and say, okay, step 6 is saying that the triangle ACD, is equal to the triangle BCD. And so, because these two triangles are equal, then the length AD is equal to the length BD. And that's by side, side, side. And so finally, step 7, we can go ahead and say, okay, well, since we know this length is equal to this length, we know that CD bisects AB. So CD bisects AB, and that's by the definition of a bisector. It divides it into 2 equal parts. Okay, so what was our goal? Bisect AB. Guess what? We did it. CD bisects AB. So we're done. But as promised, I am going to show you a second proof for the line bisector. And I'm actually going to do it on another page just in case I don't want to run out of paper toward the end of the proof and have to, finagle that situation. So line bisector proof number 2. Okay, the second proof is going to be based on the original construction, the double equilateral triangle construction. So let's go ahead and make that diagram. Here's my straight edge. So once again, let's see, I'm going to count this over. So 1, 2, 3, 4, 5. That's my middle. 1, 2, 3, 4, 5. Oops, did I do that wrong? Yep, I went over 6, so just erase that part. All right, so here's my original line. AB. And our given and goal are the same, of course, as the last one. So given line AB, the goal is to bisect AB. And step one is going to be pretty much the same, except we're constructing two equilateral triangles. So we construct equilateral triangles plural, and these will be ACB and ADB. So triangle ACB and triangle ADB. And our justification for that is, of course, the brick that says we can construct an equilateral triangle. So that's brick number 2. So B2 for brick 2. And so, again, I'm not going to construct them here. I'm just going to sort of estimate, you know, it won't be perfect, but it'll work for our diagram. And let's go ahead and draw these in. All right, so this up here will be point C, and this down here will be point D. So I've constructed my two equilateral triangles. Step 2 is going to be to, you know, draw this line CD. So draw CD, and our justification there is rule number 2. Rule 2 says we can connect 2 points, oops, right there. Connect 2 points with a line. So here we go. And now step 3, we're going to define the point E at the intersection. And that's the intersection of CD and AB. And so let's go ahead and draw in point E. Rule 1 says I can define or draw a point anywhere on my paper. All right, let's see what we got here. So this line is equal to this line, is equal to this line, is equal to this line. Okay, so because they're both equilateral triangles, we know that this is equal to this is equal to this. But since this is also equal to this, then this must also equal to this, must also equal to this. So all 4 of those lengths are equal. All right, so step 4, we're going to point out that AC equals BC equals AD equals BD. And that's based on the definition of the equilateral triangle. Well, we can see that CD is in fact itself. So, you know, obviously equals itself because it is itself. And now we can say, wait a second, the triangle CAD is equal to the triangle CBD. So step 5. We can say that CAD, let me put the triangle symbol there, is equal to the triangle CBD. And because this triangle is equal to this triangle, this angle here must equal that angle there. So the angle ACD is equal to the angle BCD. And that justification is because this side is equal to this side is equal to this side, and this side is itself, so it equals itself. So all three corresponding sides in both triangles are equal, so we'll say side, side, side is our justification for saying that CAD, triangle CAD, is equal to triangle CBD. Side, side, side. Okay, well, now I can basically wrap this up in the same way that I wrapped up the previous proof, which is to notice that I can use side angle side, right? That this length here, CE, being equal to itself, enables me to make the next logical step, that the triangle ACE is equal to the triangle BCE, because this side is equal to this side, this angle is equal to this angle, and this side is itself. So, so therefore these two triangles are equal, and therefore this length must equal this length. So the two triangles are equal, and AE equals BE, and this is by the side angle side assumption. And once again, step 7, AB, we'll say CD, the line CD bisects the line AB. And that's by the definition of the bisector. Okay, that was getting a little bit long, but we made it, right? So what was our goal? Bisect AB. Turns out CD bisects AB, so we met our goal, and we'll go ahead and write that we are done. The proof is complete. Okay, now before we move on, we want to add any bricks that we have, right? So in the last lesson, or last video, we added the angle bisector brick. Now we want to add the line bisector brick. But the question is, where does it go? So first off, if we look at this proof, we see it depends on brick number 3, the angle bisector. But this proof does not depend on brick number 3. So should we put line bisector up on top of angle bisector or next to it? Logically, you could do either one. But in general, I would say it's best form to place bricks as close to the foundation as possible, as low as possible. Okay, so we are going to put it next to the angle bisector brick. So this will be brick number 4, and this will be the line bisector. Okay. Now that gives it the appearance it's kind of hanging there. So I'm just going to extend this one a little bit. At some point we might have to start using arrows because these are not all just going to neatly fit on top of each other in the drawing. So eventually we'll probably have to start just using arrows instead of this. But I like the way this looks for now, as long as we can use it. So there we go. We have proven the angle bisector and we've proven the line bisector. So that wraps up today's lesson. But remember, if you want to learn, you need to practice, okay? So practice problems located down below in the description. Thank you for watching, and I hope to see you in the next video.